So, if I open up those notes that you have there, so let's look at this first. This we have already seen, although I guess I linked that. This was our limit definition, hopefully, at a point. And so what we were looking at is that x was getting closer and closer and closer to that fixed point, right? It might be 3, it might be 7, it might be 0, whatever it was. So x, oh, there's the wrong one. X there, we were watching as it got closer and closer and closer, and the line would get closer to the tangent line. So that was our idea that we were looking at on Friday. And whenever we look at those points, we had the point, this is just review, x, f of x, and a, f of a, where a was some number, right? And so we did slope formula with those, f of x minus f of a over x minus a. And we wanted the limit as x got closer and closer to a. That was our idea that we were looking at. So that was at a point. And I still think this is much easier to use if you have to do limit definition of a derivative at a single point. I think it is all around easier to use than what I'm about to teach you. But there are going to be times where we have to use the second one that I'm going to teach you. So, if I click on this one here, it's going to give us a new picture. Okay? So, I still have 2 points. I have x, f of x, and then my other point is x plus h, f of x plus h. Okay? That needs a second parentheses there. Where's that? Right there. Inside that. So it's correct. Okay, so what's happening is I've got this fixed point here, x, f of x. And I'm adding a value to my x. So that's this horizontal line, this horizontal green line right here has a length of h, whatever h is, right? So if my h gets smaller, right? So if I drag this over, making that h smaller, what happens to my other point that I've got here? What is happening? Can't really use the word smaller for a point. In this particular case, it is increasing, but I could change the equation of the function and it would not necessarily be increasing, but it's getting closer and closer and closer to f of x, right? So what's happening here is I'm still pretty much doing a slope formula, and I'm pretty much moving my point right here closer and closer and closer and closer to that value. All right, so let's look at what this will look like for us here. This time, the points that I'm using are going to be x, f of x. That's not changing, right? That was the same on the other problem. And then I've got x plus h, f of x plus h. So if I'm still looking at slope, right? So if I want to do slope formula with this problem, I'm going to do it this way because textbooks typically put that f of x plus h first, minus f of x, although it could be written the other way there and would still be true. And then I would have x plus h minus x. We all agree that slope formula there between those 2 points. Okay, so in this case, what we're wanting to limit here, oh no, that's wrong, it's not h. Okay, so on this graph, f of x stays where it's at, it is not changing. My h value is changing as I get closer and closer and closer to the point that I'm interested in. What is happening to that h value? What is it approaching? Something weird's happening. It's getting closer and closer and closer to 0, right? Because if I can make it to that point, then the distance between x and x plus h is nothing, right? They're there. So in this case, h approaches 0. Now, we could simplify this a little bit. Numerator you cannot do anything with. But what could you do in the denominator? The x and the negative x do cancel. There. The x and the negative x cancel. So the way that we usually see this written is limit as h approaches 0 of f of x plus h minus f of x all over h. All right, this is the general derivative. Of f right here. I'm going to write this other below it because our textbook uses it. Our textbook does not use a h. We're going to use a h in class because I think it is easier to deal with. But our textbook does this. They like to use delta x. It's your change in x, and that is your h value getting smaller and smaller and smaller. So they do f of x plus delta x minus f of x all over delta x. It is the same formula. It's just instead of h, they use the delta h symbol right there, or delta x symbol right there. So I just wanted to throw that out there in case you see it in the textbook anywhere. That's what they're doing. For that, plus they've already been giving us some delta x problems, right? They have actually been giving us derivative problems in with the limits. Those delta x problems we've been doing have been derivatives. We just didn't know we were doing derivatives yet. So that might be helpful to know because those strategies we were using on delta x problems, we're going to use those for these limits. Now, let's talk about why in the world we would use this when we could just use the other one, right? So this gives us the general derivative at any point, not just at a single point. I might have something like this. Find the derivative of f of x equals x squared. Okay? Did they say at a certain point? They did not. They just said find the derivative. Okay? So I need a derivative that can apply at any point, right? I cannot use limit definition of a derivative at a point for this problem. I cannot use f of x minus f of a over x minus a. Wish I could. It's easier most of the time. But I'm going to have to use the one that we just wrote down, the limit as h approaches 0 of f of x plus h minus f of x all over h. So this piece right here is easy to replace because it is just f of x, right? H right here is easy because it doesn't need to be replaced. You just need an H in the bottom. It's always the same on these problems. So that's easy. It is this part right here where things are difficult, right? So when we see f of x plus h, that means that we're plugging x plus h into the equation for our x. So instead of x, we are putting x plus h squared, like that. And you're going to need to like multiply that out, so I'm going to go ahead and do that. We can square, double, square. So x squared is x squared. To double the middle, we'll do x times h, and we'll double it. We'll get plus 2xh, and then square the last, plus h squared. So if I plug that stuff into my limit definition of a derivative, I will have x squared plus 2xh plus h squared minus x squared all over h. Let's make sure everybody knows where all those pieces come from. So I'm going to put a purple box around this stuff right here. That was our f of x plus h that we figured up over to the side. This x squared right here is just the formula for f of x. And then the h is just always the same on the bottom. Yes?
So why did f of x plus h equal x plus h squared?
You are taking x plus h, so you're taking this right here, and you are plugging it in where the x is at in that formula. Okay, questions so far? All right, so now these work like delta x problems. What you usually want to see happen is everything cancels that does not have an h. So this x squared cancels with this positive x squared right here. And that leaves 2xh plus h squared all over h. Since there is an h with every term in the top, we could factor an h out. So we've got h times 2x plus h in that numerator, and we've got an h in the denominator as well. Okay, questions so far? What can happen now? H's cancel. All right, then what do we have to do? Plug in. What are we plugging in for? H. So 2x plus 0 is just 2x. So the way we could write our answer here is we could say f prime of x equals 2x.
How did we do this problem here?
If you are using this formula, it will always be 0 because that h is like how far away you are from the x value. Because like on our picture here, that x is like your distance on that x-axis from the point you're approaching. So as your point gets closer and closer and closer and closer, that distance between the points is going to get lower and lower and lower. So it will always approach 0 for these. Good question.
So the instantaneous rate of change is 2x.
Yes. So what this means is I can use it at any point on the graph.
So in that case, we can plug in the x.
Right. So like if I wanted to know f prime of 1, I would plug in 1. 2 times 1 would give me 2.
So that's good.
Yeah.
So we're finding another equation.
Yes. And if I did f prime of -3, I would get 2 times -3, which is -6. And to think of it graphically, because I think that helps you see a little bit what you're talking about. if I open just a new Desmos right here, if I graph f of x equals x squared, that's very common. We all know what it looks like, right? For example, if I want to know the slope at the point, let's see, if I want to know the slope at the point 1, 1, right, then I could plug into that formula and my derivative formula, which is 2x, and I would get 2, right? So if I think of that slope right there, if I use my point slope form, which we'll practice more too, the slope is 2, and then we would have x minus 1 plus 1. Right there is my tangent line. It has a slope of 1. I'm sorry, a slope of 2 for that. But this could also be used at other points. So like if I use the point -2, 4, let me zoom out a little bit. If I'm looking at this point right here, then at -2, I would use my formula. I've got f prime of -2 would be 2 times -2, which will give me -4. That is the slope of the tangent. So if I wanted to write an equation for the tangent line, it would be y equals -4. If I use that point slope formula that we've used before, it would be x minus, our coordinates are -2, 4. So it'd be x minus -2, which will become x plus 2 plus 4, like that. So if I graph that one here, look over here, y equals -4 times x plus 2 plus 4. Oh, 43, 4. And that will give you, oh, I've messed up some. Oh, thank you. Okay, that'll give you the tangent line at that point there. So this could be used at any point on the graph. We could know the point of the slope of the line at every single point, even something like 1.573, right? I could plug in 1.573. It's going to give me the slope at that point. So you can very precisely know the slope at any point on that graph there. So anytime it just says find the derivative and it doesn't give you a point, you have to use this. If they give you the derivative and say find it at this point, you could use this because you can use this and then plug in the number. Most of the time, I find the other definition easier if it's at a point. But maybe if you have to do it for more than one point, this still might be better.
And for that other thing, if it's f of a and you're not given the y, you plug the x value that you're given into the equation.
Correct. Correct. Yes.
I don't understand where column system, if it's x or y, like if it gives you a point, which one is what I,
So,
which one I'm going to remember f of a?
so the textbook gives you a point most of the time. So in that formula, for this formula or for the other formula, x, your a value or your x value is the x coordinate. Okay. So when you're finding so for example, whenever I have the point 3, 4, something like that, this is always your x coordinates. This, a lot of times we call it the y coordinate, but we could also call it the f of x coordinate, right? So, so like if this is your a value here, this is your f of a.
X value and a is the same thing.
Correct. X value will be your a with the other problem. Yeah. In these problems, you don't replace your x with an a, so on these problems you won't use it. But.
Would you plug in, like, for f of x, plug in the equation minus f of a, you would just plug in the y value to that?
Yes, because the f of a is just the y value if it's given to you. Yeah. Sometimes it's not given to you and you have to plug in and find it for that. All right, let's do another one. Okay, we've got x to the third plus 2x. So in this case, we are using, it doesn't tell us a specific point, so we are using the limit as h approaches 0 of f of x plus h minus f of x all over h. I'm going to go over to the side and find f of x plus h because it gets a little extensive and I don't want to try to do it within the rest of the problem, but you could. Because you've got to do x plus h to the third power plus 2 times x plus h. Now, raising x plus h to the third power means that we would have to do x plus h times x plus h times x plus h, which you can do, but it's going to take a while. Does anybody remember another way we can do that?
So this is like a pretty neat thing here. You do a little box, x plus h times x plus h, take that, and multiply by x plus h.
You can. That'll be longer, though. We learned a shortcut last year.
Like pyramid thing where it's like
It is
one
the
and then
pyramid.
like 3 ones?
So that Pascal's triangle can be used. You are welcome to just make your box, multiply the first two together, and then multiply later.
Square and then just multiply that by the next one.
You can, but what if this was to the fifth power instead of the third power?
I would still doing it.
Yeah, you would take forever because especially the really neat thing about this is it's always going to be x plus h that you're cubing. So Pascal's triangle is a little harder when you actually have numbers in there, but it's so much easier for this. Like, you really do want to try to use it. So Pascal's triangle, you got a 1, and then the next one is 1 and 1, and then you got 1, 2, 1, and 1, 3, 3, 1. So each number is just the 2 above it added together, right? And so this would be 1, 4, 6, 4, 1, right? Because for each line, you're just taking the 2 numbers above and adding them together to get that number below. If we needed one more, we don't need this many for this one, but I'm going to go ahead and write it out so we've got it. You don't normally see these past like the 5th power that they're actually expecting you to do, but you might see it up to about 5th power. And I guess they could give you even higher if they really wanted. Alright, so for this would be your like 0 power line. You never use it. This will be your first power line. You also never use it because raising something to first power is easy. We generally don't ever use this for squared, but think about it for a second. What do I use for the shortcut for squaring something? Square, double, square, which is kind of like square, double, square, that double in the middle right there. So it's kind of the same thing. And then this would be to the 3rd power right here. That's the line that we're going to need. So when we do this, we're going to have those as coefficients. So we've got 1, 3, 3, 1. And then the nice thing about this is it's always just an x and an h for these types of problems. So what you're going to do is you're going to start here with x's. You're going to go x to the 3rd power, x to the 2nd power, x to the 1st power, and then you won't have an x at all on the last term. You could think x to the 0 power is just 1, right? So you don't have an x at all. So you just start and descend with one of your variables. Then with the other variable, you are going to start here with 0 h's. Then you will have h to the 1st power here, h to the 2nd power here, and h to the 3rd power here. And then you just have plus signs in between everything because you won't see a minus in there. It'll always be plus. So does that make sense? The x goes 3, 2, 1, nothing. The h goes 0, 1, 2, 3. So if we use that to expand, it's a little bit quicker. We also want to distribute this 2 right here. So plus 2x plus 2h. And then you would want to simplify if possible, but I don't think it's going to be possible on that. I think that is your f of x plus h. So it's going to look like this: x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2x plus 2h. All of this is just f of x plus h. You're going to need some room for these problems. Okay? Then you have to subtract f of x, which is x cubed plus 2x. Make sure you put some parentheses around that because that negative gets distributed to it. And then all of this is over h. We still have our limit notation. Okay? Now, what's going to happen on this every time? Anything without an h cancels. That x to the third cancels. This 2x right here cancels because that's going to be a negative when we distribute the negative. So we can do the limit as h approaches 0 of h. Somebody open that door. It's probably Hunter. I know him. Plus 3x. H. I'll get them tomorrow, Elam.
Okay.
Yeah, sorry. Plus h squared plus 2 all over h. These cancel. Anything with an h goes away because you're plugging in a 0. Sorry, guys. No h on the bottom. And so this goes away, and you get 3x squared plus 2 is your answer for that. So let's do a couple of these for our homework. Let me see what I had. Let's see. Sorry. Let's do, let me look at the problems. 15, 17, 19. Okay? So it is the same page as last night, or over the weekend. Do page 131. Let's do 15, 17, 19. I'm not going to, is somebody sending something to Lexi?
Yeah, I will.
I'm not going to change it on Canvas because we're just behind, and next year I don't want to think I just only gave 3 problems. We'll work on this some more tomorrow.